Good day. Today we will consider a vacuum gripper robot manipulator. A vacuum manipulator is an industrial robot that can be used to perform various tasks. He can pick up the workpieces with the help of the vacuum gripper and move it within working area. This workspace is the result of the robot's kinematic location and defines the limit within the robot's manipulator can move. A typical tasks for this type of robot can be divided into the following steps. Moving the vacuum gripper to a specific location. The second, capture of the workpiece. The third, transportation of the workpiece within the working area. And fourth, releasing the workpiece. In this model, we can see encoder motors for movement in the horizontal and vertical planes, and of course for rotating the robot. There are also limit switches that signal that the starting position has been reached by coordinates. A vacuum gripper is used to grip the workpiece. The compressor forces air into the system, and the workpiece is captured or released with the help of the valve. This model should work as follows. At first, the robot should reach the starting positions in all coordinates. Next will be turning and extending the manipulator. The next step is lowering the manipulator to the set point. Next, the workpiece is gripped, lifted and moved to another point. After that, the manipulator returns to the starting position. Practical part. In this Fischer Technique model, we see a more complex program. The program consists of the main program and 9 subroutines. This is due to the fact that there are a lot of processes. Let's start with a brief description of the main program. The program starts with start and 3 subroutines for 3 robot coordinates. Let's imagine that our robot was at some point from the very beginning of the program. That is, each coordinate will have its own values. Therefore, it is necessary to transfer all coordinates to the initial state for the correct operation of the program. This initial state is determined by a value of 0 on the routine's digital input. As we can see, for 3 subroutines, we have 3 zeros on the digital inputs. Let's take a closer look at one of these subroutines. This subroutine contains input and output to the main program. Another subroutine and has a digital input which is highlighted in orange. All the orange connections we can see in this software are digital. Element I3 is a limit switch for the Z coordinate. When the switch is pressed, it means that the 0 or initial position is set for this coordinate. The next element is the C3C input. This element is responsible for counting motor pulses with an encoder. The M3 motor encoder is connected to the input on the C3 controller. This element is located in the Elements group in the Inputs and Outputs section. Press the right key and select Counter and the address of our encoder in the menu. The next element is M3E. This input is not a real input, but only a logic input to control the encoder motor. And the last elements are the output to the motor and the current values according to the coordinate. The POS-EM subroutine compares the current values of the coordinate position and the set values, 0 for the starting position. Let's consider the central part in more detail. The current and set values of the motor encoder are attached to the comparison element. If you set a value with a minus sign, the program will work on output A less than B, and the motor will rotate to the right. If set with a plus sign, on the contrary, the motor will rotate to the left. And if the set value is equal to the current value, the motor will stop. The Fischer-Technique controller remembers the values from the encoder and sums them up. Therefore, for the correct operation of our program, it is necessary to reset the value of the counter in the controller after reaching the initial position. This element is responsible for resetting. In it, select distance or reset. Let's also consider one more part. If this coordinate was already in the initial position, when the program was started, the program will work along this branch. There is a wait for element here, which waits for a signal from the limit switch. After receiving this signal, it goes to the next subroutine. The end-EM subroutine is responsible for resetting the current values of the motor and assigning a value of 0. This concludes the part about setting the 0 position from this coordinate. For the following coordinates, there will be the same subroutines, only the addresses are changed. Therefore, you can simply copy an already existing subroutine and replace the addresses of elements in it. Let's go back to the main menu. After the initial position, the position 1 subroutine follows. Let's consider it in more detail. In this subroutine, we can see the subroutines already known to us for each coordinate. Here we can set the value for each of the coordinates, changing the value from 0 to 800 as an example. After reaching the corresponding coordinate values, a unit appears as the output of the routine. And when a unit appears on all coordinates, the wait for element will change its status from 0 to 1, and this subroutine will end. Let's return to the main program. The next element is pause. We put 2 seconds. This is followed by VGR on subroutine. In this subroutine we can see the following. At addresses 0, 7, we have a compressor for compressed air. It turns on. A small pause of almost a second. After that, along the vertical coordinate M2, we lower the robot by 100 pulses to capture the workpiece. This is where we can see the number of pulses. After that, the motor M2 stops and the electromagnetic valve 08 turns on, which makes the workpiece capture. After that, there is a short pause and the lifting of the workpiece in the vertical plane by 100 pulses. The next step is to stop the motor and reset the motor pulse counter. This completes the routine. Next is the position 2 subroutine, which is the same as the position 1 subroutine, but with different values for the coordinates. The same with the VGR of subroutine. The difference is that in it the compressor turns off and the valves closes. In the same way, the main program works in a cyclic mode until it is forcibly stopped. Now you can see the program in its entirety.